Non-vertical asymptotes, on the other hand, is what happens as x approaches infinity. So what we're interested in, or negative infinity. So what we're really interested in is as x approaches positive infinity of f of x, what happens as x approaches negative infinity of f of x? What happens? So it's like, what happens at the very ends? As x gets very, very big or x gets very, very small, how does the function behave? That's where the non-vertical, if it has any, the non-vertical asymptotes come in. So in our case, non-vertical asymptotes describe the behavior of the graph of f of x as x approaches positive and negative infinity. You can use limit notation if you're not super comfortable with that yet. Okay, I wrote it out in words as well. And what we're looking for is a graph can intersect, or I need to add a graph can intersect and or cross a non-vertical asymptote. That's why I wasn't like a super fan of this definition that I found online here, but does not meet, because it can intersect it. So for non-vertical asymptotes, what we're looking for is what happens as x gets very big, what happens as x gets very small. So in other words, go to a positive or negative infinity. Does the graph start behaving in a particular way? When we found Euler's value, that was an example of that. As x goes to positive infinity, that value, the function that we put into the graphing calculator, ended up getting closer and closer to 2.728, blah, 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 like the Euler's value. So that's just an example of something that has a non-vertical asymptote. And in that case, it happened to be a horizontal asymptote. And a good way for rational functions to recognize when you have horizontal asymptotes is to take and say one option is if the degree in the denominator of f of x is greater than the degree in the numerator, then the asymptote is y is equal to 0. Why does that happen? So we're going to go over here on the side and explore that for a minute. So if I look at f of x equaling, for example, let's say x over x squared minus 1. I'm just making it up, right? What if the limit as x approaches infinity of f of x. So if x gets very, very big, what ends up happening is this one grows in the denominator, grows very fast, because of the higher degree here. So grows very fast compared to everything else. And this is slower up here. So when the number in the new denominator is very, very big compared to the numerator, I'm dividing a very small number by a very big number. We're going to get values. So this is going to approach values close to 0. So therefore, as x gets infinitely big, it grows even bigger here, that x squared compared to everything else. This will approach 0. So it's going to approach y is equal to 0. The whole function is going to start behaving like as if it was just a horizontal line at y is equal to 0. That's what that means. And the same, even if I did it for negative infinity, the limit as x approaches infinity, but at negative infinity of f of x is equal to, this one is slower up here, grows fast, if I substituted in negative values for x, for example, and you could test it out, like if you wanted to let x be like a very large number, x is equal to 100,000, that's 100,000 over 100,000 squared minus 1. This number is still astronomical, even though you have 100,000 in the numerator. So this is going to be 0.000, something super close to 0. So even this one is going to approach whether it's positive or negative infinity. So the key is, as soon as the degree is higher in the denominator will always grow faster, and the whole function is going to start approaching 0, whether you're going to go to the positive or negative version of that. All right, so now What happens if the degree is not greater in the denominator? Let's say it's the same. That's still a horizontal. If the degree in the denominator of f of x is equal to the degree in the numerator, then the asymptote is going to be y is equal to the leading coefficient of n of x over the leading coefficient of d of x. That idea, just so you know, if I look at, for example, f of x, let's do something like this. Y is equal to 1 over x. As x approaches infinity, I know that y is going to approach 0. Even if you look at the parent function of this in the do now question 1, if you look toward the right, it's going to start flattening out and approaching 0. Big numbers for x, this is going to approach 0. Now, if I'm going to use that idea and I'm going to pick a function that looks like this, y is equal to, let's say, same degree, so 2x squared minus 1 over 5x squared plus 3x minus 2. And I have to look at what the limit, by the way, it's going to be the same to negative infinity. So it doesn't, I'm just going to show you with positive infinity. As x approaches positive infinity of 2x squared minus 1, 5x squared plus 3x minus 2. As x gets infinitely big, the things that get more and more insignificant, and I'll explain mathematically why it happens in a minute, is the -1 is not going to matter so much, because if we're substituting in 1 million for x, subtracting 1 from that is not going to make that big of a difference in the size of the number. And the same for the -2 and the 3x. If I'm substituting in 1 million for x, it's going to 1 million squared times 5. That minus 3 million minus 2 is not going to make a big difference in the function. And if I'm now at 100 million and so forth, the bigger x gets, the more insignificant the 3x minus 2 and the -1 becomes. So essentially, it is going to start behaving, the function itself is going to start behaving just like this part here. Now, that means then that you end up with something it behaves very, very closely to 2x squared over 5x squared. And 2x squared over 5x squared, the x squares cancel out and you get 2 over 5. So then the asymptote would be 2 over 5 for that. If I was going to prove it to you algebraically, I can take the limit as x approaches infinity of 5x, no, not 5x squared, sorry. It's going to be 2x squared minus 1, and down here is the 5x squared plus 3x minus 2. But I can multiply both the numerator and the denominator by 1 over x squared, 1 over x squared. So essentially, I'm multiplying every term in the numerator and the denominator by the highest degree of each of those terms. So that's going to give me the limit as x approaches infinity of, sorry, my iPad is being a little hokey. The first term is going to be 2 minus 1 over x squared. And the next one is 5 plus 3 over x minus 2 over x squared. But as x approaches infinity, this one here, well, it's 1 over something that grows very big, is going to approach 0. So that little piece there is definitely going to approach 0. This one, you have 3 over something very big, is going to approach 0. This one is going to approach 0 even faster. So in other words, you end up with something that ends up looking like 2 minus 0 over 5 plus 0 minus 0 is just 2/5. So that means, oh, as x gets very big, this will approach 2/5. It's not saying it is equal. That's why I have the limit there in front. It's not saying that it is equal to 2/5, but it will approach it and get infinitely close to it. The bigger x is, the closer it becomes to behaving like y is equal to 2/5. So that's why when I wrote this over here, that if the degree in the numerator and the denominator are equal, the asymptote is going to be y is equal to, and you just take the leading coefficient over the leading coefficient. Slant asymptotes, or by the way, they're also called oblique asymptotes. that's an alternative name, happens if the degree in the numerator is exactly 1 degree higher than the degree in the denominator. Then the asymptote is going to be y is equal to q of x. And I define q of x. Oh, I didn't realize I wrote on top of this in here. I defined q of x as the quotient and then this is going to be the remainder. So here, if I take and divide n of x by d of x, remember I can write it as quotient plus remainder over d of x. So it's a rewriting almost like a mixed number, right? Like that. And what ends up happening is that d of x is going to have a higher degree than the remainder, and therefore as x approaches infinity, the remainder piece drops out. And I'll show you in an example in a minute. So that's exactly 1 degree. So if it's exactly 1 degree, this is going to be linear, your result, if the numerator is 1 degree higher than the denominator. For nonlinear asymptotes, so it doesn't always have to be a line if the degree in the numerator is at least 2 degrees higher. So exactly 1 degree higher is linear asymptote. As soon as you get above 1 degree, so 2, 3, 4 degree higher, you end up with something that's nonlinear as an asymptote, which is also okay. So that's why those two definitions that you probably found online are a little wishy-washy, because asymptotes don't always have to be lines. And most of the stuff you find online, it describes asymptotes as linear, because that's what you see most frequently. So we're going to jump right in. And by the way, the way to find the actual asymptote here is exactly the same for slant and for nonlinear. You take and divide the numerator by the denominator, and then the quotient itself is going to be your asymptote. All right, let's try a couple of examples. So the first one here, and that's really hard to see, but the denominator is actually a degree 3. So if I look at this and it's asking for the non-vertical asymptotes, we're just looking for what is the degrees in the numerator and the denominator. In this case, the denominator has a greater degree than the numerator. I know that the asymptote, the non-vertical asymptote, is going to be y is equal to 0. That's a horizontal line. For part B, the degree in the numerator and denominator are the same, so I know that the non-vertical asymptote is going just to be the ratio of the leading coefficient, so that's going to be 5 over 2. Now for the next one, it has a degree 3, and the higher degree is in the numerator. So when that happens, for me to find the non-vertical asymptotes, you have to divide. So divide. So in this case, I happen to do a binomial, so I can use synthetic division to do that. I get -2 here, 1, 7, -3, and 5. Carry down the 1, -2, 5, -10, -13, 26, and 31, I think. So if you can imagine, I'm going to rewrite h of x as x squared plus 5x minus 13 plus 31 over x plus 2. But if I'm taking the limit as x approaches positive or negative infinity, it works the same to negative infinity. The limit of h of x, what ends up happening here is this part here, just that piece, is going to approach 0. The reason why that's going to approach 0, just that little piece there, is because the degree is higher in the denominator than the numerator. So that little piece will approach 0. So that means h of x will start only behaving like the quotient out here. So remember, this is q of x. This is the remainder, and this is d of x down there. So what ends up being the asymptote is y is equal to x squared plus 5x minus 13 for that. So if the degree is higher in the numerator. So you got to do a little bit of division. In this case, the denominator happens to be binomial, so we can just use synthetic. If it wasn't, we would have to use long division.